So we are back again with Bash. I got another fun one for you. Today, we're going to try and implement the base64 algorithm, both encoding and decoding in pure Bash. What I mean by that is we're not going to fork out any external utilities. We're not going to like OpenSSL or the base64 that comes with our system. We're not going to, fork out to Python or whatever. We're going to do it all using nothing but Bash built-ins and its built-in mathematical facilities. Mathematical facilities, like the nerdiest I've ever sounded. We're going to use all the built-in math that Bash has. Now let me just get this disclaimer out of the way, okay? This is for educational purposes only. Don't use this. It's going to be slow. I'm going to do my best to not have bugs, but it's going to be slow. Just reach for the ones that come with your system. They're going to be so much faster. This is just to make a fun video for entertainment purposes, but it is going to work. We're going to write tests for it. We're going to make sure it works how you would expect. And it'll kind of be fun to benchmark it and see, how fast does this thing actually work? I anticipate some of the biggest problems will be, like a lot of the other things I've written in Bash, reading and writing binary data. We can do it, we're just gonna have to do a couple little translations to make it possible. So yeah, let's just jump into it. Let's make a new directory that we can work out. We're gonna call this bash base64. There we go. I'm not gonna talk about the algorithm yet. I'll talk about that as we get to it. I wanted to tackle this the way that I tackled my pure bash MD5 video. If you haven't checked out that video, go check it out. It's a really fun watch, a ton of fun. And we're gonna be using some of the techniques I went over in that video. You won't have to have seen that video to understand it, but I just wanna let you guys know that we're gonna tackle this the same way. What I mean by that is we're going to write tests first. So we're going to have a program here. Ideally, we will have a simple program called base64, and it will be a bash script, and this will actually do the decoding and the encoding for us. So our basic base64 script will do something like implement me. Okay, that's our placeholder script. So I'm imagining that when we run this script, like base64, we'll be able to give it a file like this, and it will decode that file. Oh, that breaks because it doesn't exist. We'll give it a file like this, and it will actually encode that file as base64, and then we'll run it with a -d flag, and this will decode that file from base64. But before we implement it, let's write some tests. So we'll have test base64, and this will be a program we can run to make sure that everything's working as expected. And the nice thing here is we can kind of program against this. We can program a little bit, we can run the test, program a little bit, run the test, and make sure everything's kind of working how we expect. Let's just stub this file out for now. Echo to do need tests, and then exit with 1. So it's a failure. So if we run our test program now, we can see that it fails. I'm not actually showing the exit code on the prompt, but there it is. Why am I doing that for now? Because let's go make some files. Base64 can encode and decode data. So we're going to store that data in files, and we're just going to loop over them as part of the test. So we'll make dir files, and this will sort of be our test fixtures. So if we go in here, we can see that we currently have no files. Let's go ahead and make some. We could make an empty file, .text. When you base64 encode an empty file, you get an empty string. So this will be a pretty simple test. We're gonna make another one where we'll echo hello into hello.text. So this will have HELLO. It will also have the line feed here, so that new line will be part of the file because it was emitted by echo. And then I'm gonna do what we did last time with the MD5 video. We're gonna create a random 4 kilobyte binary file. It's going to have, just gibberish in it. It's not going to be suitable for outputting as text. It's just going to be random binary data, which will include null bytes that we'll have to process with bash. So we can do that really simply. We can say dd if equals dev urandom of. This is our output file, random 4 kilobyte dot bin. We can just say a block size of 1 kilobyte and a count of 4, and write, I think this wants a K here. There we go. I always do that. I always put like KB and it wants K. Sometimes it yells at me when it's lowercase versus uppercase when I go across different operating systems. Different DDs kind of work differently. But if that worked, we should have 3 files now. We should have our empty file, which is 0 bytes. Hello, which is 6 bytes because HELLO is 5 bytes plus the new line. And then we have this 4 kilobyte exactly just random data. So if we take a look at it with a hex editor, you can see we do have some null bytes showing up in there randomly, which is good, cool, awesome. Just randomly generated nonsense data. So our goal here is to be able to encode the files as base64 and then also be able to decode them back. I'm going to tackle encoding first and then we'll deal with decoding, but our goal is to be able to go both ways because the algorithm does have that symmetrical property. Once you encode it, you can just decode it back to the original data. It's not like an MD5 where it's a one-way calculation. So I've talked a lot. Let me actually show you what that looks like. So if we cat hello.text, you could pipe this to base64. And here is the base64 encoding. Now, have you ever seen this? It might be a little bit weird, but what it does, I'll go over the algorithm more later, but it turns any sort of input data into output data that is printable. So it's printable characters. You can see there's some lowercase letters, there's some uppercase letters, there's some numbers. There's also 2 other characters, was it a plus sign and a slash, I think? Yeah, I think a plus sign and a slash is also valid. Those are your 64 possible characters. You might also see some equal signs, and I'll go over all that. If we were to cat the empty file and pipe it into base64, we get absolutely nothing. So that should be simple enough to implement. And then if we cat our random 4 kilobyte file and pipe it into base64, we get a lot of data here. But look, it's all printable. There's no weird characters. It's uppercase, it's lowercase, it's numbers. There's some slashes in here. And there are some, look, there's even equal signs at the end. That's the padding that shows on the end. And there are some plus signs. We can also pipe this to, I think we could highlight the plus signs. Oh, it's going to want a regex. I'll have to escape it. There we go. You could highlight the plus signs, or we could highlight the slashes, and they show up like that. In case you're curious, the highlight command is actually just an alias I have, so alias HL. It's ripgrep with the -- paths through option. Super useful for highlighting data, because I could do something, I think I could do like highlight 0 through 9, and then it highlights all the digits as they show up here. Super useful command. I love it. But like I said, the beautiful thing here is that if we were to take, let's say, the MD5 of this data, we get BC, F8, 14, yada, yada, yada. If we were to pipe this to base64 and then pipe this to base64-D for decode, so we encode it, we decode it, and then pipe this to MD5, take a look at this. We get the exact same data out of it. So we can encode the data and then decode it back to its original data. MD5, we get the exact same thing. So this is what we are going to implement. So to get started here with the test, what I want to do is I want to go through all these and generate what the base64 data looks like. And the reason I'm doing that is because then we can test to make sure our encoder spits out the exact same data. So we're going to use a known good working version of base64. It came with my system, super easy. So we can just base64. You don't need to cat into it. You could also base64 just empty.txt. I lied to you. Apparently you need -I here, and that one's empty, so that makes sense. I really thought you just gave it the name of the file. I guess I wasn't aware of the -I. Maybe different versions are different. I guess I've always done it like this, where you just read it in from standard in like that. So this will generate the base64. I'm going to store this back in hello.text.b64. And then we're going to do the same for the other one. So empty, spoiler, it's not going to have anything in it. We already know it generates an empty file. That's super cool. And then base64, the random 4 kilobyte bin file. And we're going to store that as random4kb.bin.b64. So there we go. For every file we have in here, we also have a .b64 variant. This way we can check our work. So let's go ahead and actually start writing those tests. So we have our test base64 program here. Let's go ahead and start implementing some of those tests. We'll do a simple for b64 in star files star.b64. We're going to loop over all of the b64 files because we know if those exist, also the other file will exist for it. And then we'll do some work based on that. So we'll get the plain file, this is the file that hasn't been base64 encoded, by looking at the b64 file and stripping off .b64 from the right-hand side of the string. So what that means is if we were just like echo plain here, let's echo b64 arrow to plain, I'll show you what this looks like. So if we run this, and then we run test base64, you can see that we loop over empty text.b64, which gives us empty text. This gives us this, and this gives us this. Hey, cool, that's awesome. Let's actually make this do something now. Because for every base64 file, we have both the base64 file and the plain file. We need to actually check. So let's test encoding the file. So we want to run base64. We want to read in from the plain file, and we want to write it to a temporary location. We're going to write it to a temp file, and then we can check that temp file versus what we actually have, what actually exists on the file system. So let's make a nice little temp file just so we can use for our own testing purposes. We could say temp equals /temp/ bash base64 $. This is our PID. Doesn't really matter. I don't assume too much stuff is going to clash here. If we are going to make a temp file, like if we were going to touch temp, we should probably be good and set up our script to delete this file at the end of execution. So we can do that by making a cleanup function. So cleanup here. The cleanup file will simply remove the temp file with the -f, so we'll ignore any errors. We'll just do it forcefully. And then we can trap cleanup for exit. So now when the script exits, we will clean up this temporary file. It'll be gone, but we're going to use this file for our own benefit here. We can write that out to temp. So now we have encoded our plain data into a temporary file. Now we need to compare the two files. You might have heard of the diff command. You can use this to get the differences. There's also CMP. CMP is a super useful command, which allows you to... Oh, interesting. Is it part of OpenSSL? I don't even know if I knew that. I wonder if it's like that on Linux. What? Yeah, why am I getting one SSL section first? What? That's not right. That's not even the command I'm looking for. man1 CMP. This is what I'm looking for. I'm surprised that one came up first. Super interesting. The comp utility compares two files of any type and writes the results to the standard output. By default, comp is silent if the files are the same. If they differ, the byte and line number at which the first difference occurred is reported. This is how you compare two files to see if they're the same. It's the opposite of diff. It's super useful here. So now we can just compare the temporary file to the base64 file and wrap this in an if statement. So if we compared these two files together, then echo okay, else echo fail. And there we go. That's as simple as that. We can do some other things here. We can specify a code here. We're going to assume that the tests pass by default, so code equals 0, and then we'll exit the code down here. And in the event of a failure, we'll set code equal to 1. So we'll still continue on and run all of the tests, but we will keep track of the fact that we failed. Let's move this up here, and let's do this. Echo this, testing, plain, ... space. Actually, test encoding, plain, ... and then we'll run this. And we are using, in this case, we are using the base64 command that's with our system, so this should work. We'll eventually swap this out to be our bash script, but for now, we're just going to use the built-in one because then this will work, this will pass. So let's go ahead and run our tests. And look at this. We're going to test encoding this, and we got okay. Test encoding this, and we got okay. Test encoding this, we got okay. We should get okay. We know that version of base64 works. That is super great. There is one issue. Think about this. If this were to fail, we don't actually do anything with the exit code here, and we would just write nothing into that file. So technically speaking, when we test the empty file, it'll be true, even if this command fails. So we can put this in the if statement alongside this command. So I'll show you what that looks like. We'll put the if here, we'll join these two lines together, and we'll swap this for an ampersand, ampersand. So now look at this. If we are able to successfully call base64 with our input file and write it to this temp file, and we compare the temporary file to the good file, the expected file as we could put it, if both those things are true, then we echo okay, otherwise we fail. So this will fail if the files are different, but it will also fail if our base64 command fails to run, which is good. That's what we want. That's perfect. So now, this is simple enough. We can just copy and paste this logic and move it down here, and then we can test decoding plain. And to decode, it's very simple. We just want to use base64 minus D to put it into decode mode, and we're going to decode the B64 file, and we're going to compare it against the plain file. So we just have to swap those two things. But if we run this now, take a look at this. Everything is okay. Oh, that's a little bit confusing. It outputs the same file name. Hold on. I actually kind of want, if we're going to decode the file, we should be decoding the B64 file. Yeah, I think that makes more sense. So now we're encoding the .text, we're decoding the .b64 for .text, we're encoding this, we're doing this, we're doing this, we're doing this. Beautiful, awesome. We have a test harness that works now. How beautiful is this? So the next thing we can do is, instead of using the system base64, let's use our own implementation of base64, our bash script version of base64. And we run it, and it fails. But that's simple enough. That just means we have some work to do, okay? Let's actually start implementing this thing. We got the test ready. We know what our happy path looks like, so let's go ahead and get there. Also, before I move on, I also just want to show this. You can just totally like echo hi and pipe it into base64 and get this, and then pipe it into base64 minus D and get this back out of it. We'll probably be using this. Instead of having to run all the tests over and over again, we can just use this simple example instead of having to churn through a 4 kilobyte file, because I don't actually know how long that'll take. It could take a while. Hopefully it doesn't, but it could take a while. So we might just be using this to do some really, really simple basic testing. And this is good because you can always just add another byte and you'll get some padding. So in the first example, we had no padding. This one has 2 equal signs of padding. This one has 1 equal sign of padding. This should have 0. This should have 2. This should have 1. It goes like that. It goes in a pattern. So now is when I tell you guys about the actual algorithm behind base64, right? Not quite. Hold on. We actually need to be able to do something even more basic than that. We have our base64 script here. We need to be able to read the data from the user. Yeah, I can type. That's really good. Read the data from the user. We need to be able to read the data from the user, and this might include binary data. Now, if you've watched my videos before, you know that we have done this. In my previous video where I talked about making a pure bash MD5 implementation, we spent a while perfecting that. So I'm going to do what every good engineer does, and I'm going to copy my code from Stack Overflow. No, I'm kidding. It's 2026. I'm going to go ask Grok. I'm joking. We're going to go pull some of my old code from that. We've already written it, MD5. I've written it on the video. Go check out the old video if you want to see it. We're going to pull some of that code because it works and it works well, and I can explain it. And there's some stuff I actually want to go over with it. So I'll show you what that looks like. So here's the MD5 script. There is a lot going on here. Go watch that video if you're a little bit confused. I'm not going to go over all this. Don't worry. But we have a function here called process input that we want. This was our amazing function that can read data from standard input and correctly break it and check for null bytes and do everything we absolutely need to do. So I'm going to copy this code and bring it in to our script here. So now we have a function called process input. There was something else we needed for this function to work, which was all the way at the top of the script, which was lc underbar all. We have to enable this. This tells Bash that we are in byte processing mode. We're not doing UTF-8. We're not doing any sort of language stuff. We are processing data in the C locale, which means byte by byte. That is all we are doing here. That is what that signifies. So let's go down here. Let's clean this up. Let's close that function. Let's make a nice little main function. Actually, you know what? Let's go to the previous MD5 script and let's just steal this main function because I actually want to clean it up a little bit, okay? So we'll go over here, we'll steal it from the MD5 program. So I'll show you what we have. We have this function called process input. I haven't gone over this yet. Don't worry, it's not even gonna work as written. I will go over this with you, but we're not going over right now. We're gonna go down here and we're gonna look at the main function. So we have main, we call it with our arguments, that's beautiful. Main gets called up here. We take a file name as $1. And then we check if the file's set, we call process input with that file. If the file is not set, then we call process input with no file being redirected. So then it will default to reading from standard in. So we're going to want to do things a little bit differently here. We actually need to process arguments. If you remember, our program needs to take a -D to put it into decode mode. So we have to actually, before we do any of this stuff, we have to process arguments here. We can do that with getops. While getops, the options that we want to take, we're just going to take D for decode now, nothing else. Opt. Do case opt in D, and then we'll do something there, close the case statement, close the while loop, and then shift the options over by opt-in -1. This is just stuff I've committed to memory. This is how you do argument parsing in Bash. Because we're in a function, we're going to want to set opt-in, opt-arg, and opt as local. Opt is what we've defined right down here. So this might be a little bit confusing, but this is how we parse options in Bash. This will let us handle the -D option. We don't do anything with it yet. And then when we get down here, file will still be $1 because we have shifted all those arguments away. Super simple. We could do, I'm trying to think of how to handle this. Because this is going to be a program and we're going to use a lot of different functions here, I'm going to opt for a global variable. They are simple enough to use, called decode. We're going to have a mode that tells us if we're in decode mode or not. By default, we are not in decode mode. But when we go down here and we take that -D flag, then decode equals true. Now we are in decode mode. Also, while we're here, we should probably just return 2. If you give me any other sort of option, that's a usage error. That's what I'm thinking. We could come up with a usage error eventually, but for this, I think it's just simple enough just to return a failure, basically. So now that we're down here, we have this call to print hash. That's not relevant. That is for MD5. We check if the file is set, then we call process input like this. If it's not set, then we read from standard in. We're also calling this debug function that doesn't exist. I'm going to take it out for the time being. We may re-implement it if we find it useful, but for now I'm going to take it out. Here's the cool thing. I mentioned this in the MD5 video. I said instead of having to do this if statement, you could do this. Use $1, and if it's unset, use dev standard in. Now I said I wanted to stay away from this because your system might not implement dev standard in. I wanted to make this as portable as possible. And a couple of commenters remind me that, don't worry, if this file doesn't exist, Bash emulates it. So even if this file does not exist in your system, you can use it like it exists in your system and Bash will just emulate its behavior. So this is fine. This is totally valid. So with this, we can get rid of these if statements. Thank you, commenters. And this is good enough. So we call main. Main goes up here. It processes our arguments. We are either in decode mode or we're not. We get a single file or standard in, and then we call process with that file or standard in. Beautiful. So let's actually go up to the process input function. Like I said, I've implemented this before in a previous video. I don't want to go over all the specifics here. If you're interested, go check out that video. But I do want to talk about it a little bit because a lot of you guys had comments about it. I'll get into that when I get to it. Let's get rid of these calls to debug because, like I said, I got rid of them. We also keep track of the byte count. This was how many bytes we have read. That was relevant for MD5. That is not going to be relevant for base64. So we can go ahead and get rid of them. Look, we are making the code simpler. How nice is that? Like, we just keep getting simpler and simpler. What we're doing here with this code, I'm going to walk you through it. We put ourselves immediately into an infinite while loop. Then this is the main bulk of the code, and there's a lot of stuff that goes into it, and it takes a long time to get there. For this call to read, we set the IFS equal to nothing. This tells the read command, don't do any processing or transformation on the data that's coming into it. We're not trying to split it at all, okay? Then we give it -r. This tells read that we don't want to do any backslash mangling. We want raw backslashes. -r you kind of think of as raw. -d with an empty string says that, hey, our delimiter, when we're done reading, is when we hit a null byte. And we also, -n, we only want to read at maximum 4096 bytes, and we're going to store it all in a variable called chunk. I threw a lot of you there, but what this means is we are going to read the input data, whether it comes from the file or standard in. We're going to read up to 4096 bytes or up to a null byte, whichever one comes first. Then we also get the return code of read, because read can fail or it can be successful. Read is successful if it goes all the way up and reads 4096 bytes and there's still more to be read, we're not at the end of the file, then it's a success. If we have read up to a null byte, maybe it's only 5 bytes, but we're not at the end of the file, it is a success. If we get to the end of the file, then read gives us a failure. We also will get failures if something's wrong with the file, if there's some sort of like transient error or whatever. We're not dealing with that, but read will be successful if there's still more data to read. So read will be successful when it's telling us like, hey, like I was able to read successfully, there's more data waiting for you. And then it fails when there is no more data waiting for us. But it might have read some, it might have read 20 bytes and then failed. So we have to process the 20 bytes before we deal with the failure. That's why we do everything in this order. Now, we loop the chunk and we process it byte by byte. Notice this line right here, we're getting the length of the chunk. This is how many characters we were able to read into the string. This is a very important distinction because it's not saying how many characters were read. Say we read 7 bytes and the 7th one was a null byte. This will be of length 6. So you have to be careful with that. This will only be of length 6, but we might have actually read 7. And if it's less than 4096, but it was a successful return code, then we know that there was a null byte that we're going to have to manually process. I'll dig more into this later, but right now we loop over the data we've read in. For I is equal to 0, I is less than the length of the data we have waiting for us in this variable. Then we will extract that single byte out. We're using substring notation to extract that single byte out, and now we're turning it into a number. So we have like the ASCII representation of the byte. We want the raw number that makes up the byte. This is the syntax to do that. So we turn it into a number by putting a single quote in front of the name, or in front of the variable, and then we store it into a variable called C, and then we call process byte on C. So C will be a number between 0 and 255. We haven't made the process byte function. We'll deal with that when we deal with it. But right now, this will call a function with a number between 0 and 255, especially if it's in here. It can't be a null byte because bash can't store null bytes in strings. So it'd actually be 1 through 255. After we've processed that data, then we check the return code of read. If read fails, we are done processing, we break out of the loop. That is our end condition. That is our condition to be done. But if read was successful, then we have to check. If we successfully read something, but it was less than the amount of data we wanted to read, then we have to artificially throw the null byte in there that was stripped off of the data. So I know this might be a little bit confusing, but if we weren't able to read as much as we wanted to read, but read still says there's data there, that means we hit the delimiter that we were looking for, the null byte, and bash is going to skip over that, so we have to manually reinsert this 0 byte. So that's what's going on here. A lot of you had comments on my MD5 video where you brought this up, and you were like, Dave, I think this is going to break. What if you have a file that's 4095 bytes and the 4096 is a null byte? Or what if you have a file that's 4096 and the 4097th is a null byte? There were all different variations of this. Some of you updated your comments, which I thought was really awesome, where you're like, oh no, this actually will work. Others were very confidently incorrect about this. Here's the thing, guys. My code's open source. Just pull it down and test it. If you find a bug, let me know. I'd be more than open to hearing that. But as I've reasoned through it, there are no bugs here because it's a little bit confusing. The length of the data we have is not the same as the return code of read. If you're thinking like in C, where you look at the read syscall and it's like, oh, read was able to read 8 bytes, so it gave us back a number of 8. But imagine that 8th byte was a null byte. This will actually be 7. We will be off by 1 here. So that's why we have to account for it with this logic down here. And here's the beautiful thing. We don't even need to reason through this together. I can just prove it. Let's just go prove it. Let's have some fun. We're going to take a bit of an aside here, and I'm going to go into my bash MD5 program here. So like I said, I won't bore you with the details, but you can call MD5, you can give it some information, and it will calculate the MD5 checksum. No different than like MD5 sum on your system might do, and you get the exact same data. Notice that MD5 is completely written in bash. Beautiful. Again, I'll link the video in the description for anyone who wants to watch it. This is where we pulled all of that logic from. So here's what I want to do for you guys. Let's just go ahead and test these theories, okay? Let's make dir test, cd into test, and we're going to make some files, okay? So a bunch of you said, what if you had a file with 4095 characters and then the 4096 with a null byte? Let's go start creating some of this. In order to create that, we're going to need a little helper here. We can use printf. I'm going to show you some really gnarly syntax. %.0s. So this is a string formatted to show absolutely nothing. So if I give it the string hello, it prints nothing. If I give it nothing, it prints nothing. If I give it this, it prints nothing. Why is that good? Because I can put a character here like A, and then when I print it, it just prints A. Why is that good? Because I can do this, 1 all the way up to 20. And now we have 20 A's. I can do 1 all the way up to 50, and we have 50 A's. We have a function that basically yells at you. How nice is that? This is convenient because I could make this go up to 4095. That's a lot of A's. We can verify this, 4095, pipe that to word count minus C, and we have 4095. So let's go ahead and put this into a file, okay? We'll call this no null 4095.dat, just for arbitrary data, okay? So that is no null, and it has 4095 bytes. Let's go ahead and make this 4096, and let's write this out to no null 4096. Let's go ahead and make this all the way up to 4097, and let's say this has no null 4097. You see what's going on here? Now, let's generate the same things, but this time, let's omit a null byte at the end of it. So we'll do 4094 here, and then we will also printf a null byte here. We'll put these in curly braces, which will group the commands together, and now we can redirect it to null 4095.dat, because the 4094 here plus the 1 from the null byte, that's where I get 4095 from. Beautiful. Now let's do 4095 here, so this one has to be 4096. Could I have scripted this? Yes, absolutely, but I'm just showing you guys real quickly how we're doing this, and this will be 4097. Beautiful. Let's do an ls-lh on everything here. And look, they all get rounded up to 4K. Yeah, that makes sense. It's because we're doing H here. So look, no null 4095 is 4095 bytes. No null 4096 is 4096. This is 4097. Beautiful, null 4095. We can prove this. We could do XXD on, let's say, null 4096, and we can see the null byte is sitting there nice in the 4096 position. Beautiful, awesome. If we do this with 7, it should just be wrapped around to the next line. Here we go. So, to prove that this works, I'm going to back out of here. We're going to use the MD5 sum from the system, and we're going to run this on all of the files in test. I think I just called it test, right? Yeah. There we go. So here are the MD5s using the good version of MD5, not my bash version. This is the one that came with my system. Now we're going to compare my bash version. My bash version doesn't take multiple arguments, sadly, so we're going to have to write our own little loop. For f in test star.dat do echo -n $f, and then we will output the MD5, the bash version of MD5, reading in from that file. Done. And there we go. It's calculating them all. So let's take a look at this. No null 4095 is 4E84BED. This one is 4E84BED. This one is 82. You know what? Hold on. Let's make our lives easier, okay? Let's make our lives easier. Let's format these exactly the same. Instead of echoing the file system, yeah, let's just make this easier. We'll just put a tab here. There we go. That's a lot easier to read. And then let's do the system MD5 sum here. So there we go. And let's do our bash MD5 here. And now we can compare them because it should go in the same order. 4E84 bed, 4E84 bed. 82A73, 82A73, BDF9E, BDF9E, 36753, 36753. You guys see this? It all lines up. So The bash code successfully handles this. I know it's confusing. If you're coming from the world of C, you're probably thinking of the read syscall, which returns the actual SIST, the number of bytes that has been read. In our case, we don't have access to this. We just have the length of the string that is storing the bytes that may or may not have been chopped off with a null byte. So we have to make room for that effectively. So a bit of a side, a bit of a tangent. I'll put chapters in the video so you guys can skip over this if you don't feel like watching it. Let's get back to the fun stuff here. We haven't even started implementing base64, have we? So we have a lot of stuff in place. We have a whole test harness that breaks because we call process byte and it doesn't exist. That's cool. Let's not call that test harness again. And then if we go in here, we have a nice little main method which takes a -d argument. We call process input. We go up to process input. It does all this logic for us and it calls process byte with a number that represents the byte of the data that we have read in. Beautiful. Let's implement process byte now. Cool. Simple. Awesome. Now I want to keep things really simple. We could be in two modes. We're going to deal with encoding first, then we'll deal with decoding. But for now, we can say if $decode, if we are in decode mode, we will call process byte decode. We will make a whole separate function for this where we will give it the byte here. And in fact, we should probably go define the byte, shouldn't we, as $1 because it'll be given to us as an argument. And then we'll have a second function called process byte encode, which will handle the encoding, which will just be the else branch of this. So a super simple function where we call process byte no matter which mode we're in, and it will figure out which one to dispatch it to effectively based on our implementation. So let's do process byte encode will be a return 1. Let's just make it a failure for now. We're kind of stubbing these out. And process byte decode. So for our encoding function, this is the thing we care about. We have to figure out what do we do when we have a byte and we're trying to encode it as base64. And can you believe it? Now it's time to finally explain the base64 algorithm. We've made it here this far into the video. Oh, fun. So as always, check it out. Bam, we got the RFC. The RFC for base16, base32, and base64 data encodings. RFC 4648. This document describes the commonly used base64, 32, and 16 encoding schemes. It's also discussed the use of line feeds and encoded data, using of padded encoding data, use of non-alphabet characters encoding data, use of different encoding alphabets, and canonical endings. There's a lot of stuff here. We're going to implement just a very simple version of this. Because there's URL safe ways of doing this. There's 32, 16. We're just going to deal with simple base64, and we're going to pad it with just simple equal signs. So the idea here is that we're choosing an alphabet for this. We are going to turn the input bytes into a form of representation. We're going to encode them into 64 possible characters that are shoved together. And if we go down here, we can see for the base64 encoding, the base64 encoding is designed to represent an arbitrary sequence of octets, so 8 bits, like a byte, a simple byte of data, in a form that allows the use of both upper and lowercase letters, but that need not be human readable. A 65 character subset of ASCII is used, enabling 6 bits to be represented per printable character. So this is really cool because that means it only takes 6 bits to represent a character and we're representing 8-bit bytes. So what you have to do is you have to figure out, okay, well, what do they have in common, or what is the least common multiple of 6 and 8? It's 24. We'll get to that. I'm jumping ahead. The encoding process represents 24-bit groups. The encoding process represents 24-bit groups. Hey, look at that. The extra 65th character, the equal sign, is used to signify a special processing function. It's basically padding. That's how we're going to be using it. The encoding process represents 24-bit groups. Remember, 8 and 6 of input bits as output strings of 4 encoded characters. So processing from left to right, a 24-bit input group is formed by concatenating 3 8-bit input groups. These 24 bits are then treated as 4 concatenated 6-bit groups, each of which is translated into a single character in the base64 algorithm. This might be a little confusing. I'll break it down later in the video, but basically we're going to take 3 8-bit numbers, shove them all together, which will give us 24 bits, and then we're going to pull 6 bits out of it, 6 bits out of it, 6 bits out of it, 6 bits out of it. We're going to turn 3 input bytes into 4 output base64 characters. That's what we're doing. And then decoding is the opposite of that. Super easy. Each 6-bit group is used as an index into an array of 64 printable characters. The character referenced by the index is placed in the output string. So when you pull those 6 bits out, if it's a 0, it's going to be an uppercase A. If it's 1, it's going to be B. 2 is going to be C, etc. Look, it's all the uppercase letters, then it's all the lowercase letters, then it's all the numbers, and that brings us to 62. Then we have plus and slash. Those are the 2 extra characters that are thrown in there. And then, of course, we have that equal sign that's just used for padding. It's not in this list of 64 characters. Special processing is performed if fewer than 24 bits are available at the end of the data being encoding. A full encoding quantum is always completed at the end of the quantity. When fewer than 24 input bits are available in an input group, bits with the value 0 are added on the right to form an integral number of 6-bit groups. Padding at the end of the data is performed using the equal sign character. Since all base64 input is an integral number of octets, only the following cases can arrive, and it describes the 3 cases that we we've actually seen earlier in this video. So if it's an integral multiple of 24, then we will have no equal sign padding. If it's exactly 8 bits, then we'll have 2 equal sign padding, and then we'll have 1 equal sign padding. Remember how I kind of showed that a little bit? We can recreate that if you guys want to see it. If we were to echo just a single character, let's just do printf actually. Let's just printf a single character into base64. We can see that as 2 equal signs. If we put a second byte there, we can see that as 1 equal sign. And if we put a third byte there, it has no equal signs because it's a multiple of 24. 1 byte per character, 8 bits. So this is 24 bits right here. So it encodes nicely into 6-bit numbers represented as 4 letters from the alphabet. How cool is that? So whenever you have a multiple of 3 bytes going in, you will have no equal sign, X, Y, Z, or XFZ, because apparently I typed it wrong. Doesn't really matter what you type in. As long as it's a multiple of 3, you won't have any equal signs. But if it's, off by 1, then it has 2 equal signs. If it's off by 2, then it'll have 1 equal sign. So just looking at the equal signs, you can actually figure out how much padding is there, which is kind of cool. So believe it or not, this is it. This is all we really need. I did find this Wikipedia article. I do find this super useful. If you're having trouble following what I say, here's the lookup table. It's pretty simple. We're going to create that in Bash. But it might be a little bit difficult because I'm describing bits at you and I'm not actually showing you anything visual. Here's something visual. If we were to encode MAN, capital MAN, this is 3 bytes, so it's easy to encode. In base64, these are the byte values, 77, 97, and 110. This is what they look like in binary. So if you pull 6 bits out of it, that's the number 19, and that will be T in the base64 alphabet. That's all that's happening here. It's super simple. So let's start implementing it. How hard could this be? Famous last words. All right, so we'll pull up the base64 script here. We have process byte encode. So let's go ahead and let's get rid of this error. Let's grab the byte because it's being passed as the first argument. Now here's the thing, with MD5, we needed to store 64 bytes before we could even do something. We're gonna have to do the same thing here. We're gonna have to store 3 bytes. We can't do any meaningful work until we've encountered 3 bytes or we've encountered the end of the file. Then we have to drain like whatever buffer we have. So we have to store these bytes in a block. So we're going to make a global variable. This is just like what we did with the MD5 video, but we're going to make a global array here called block. And then we are going to push the byte onto the block. So now we have an array that will grow whenever we encounter a new byte. And then we'll do a nice little check down here. If the length of block is equal to 3, that means we have enough bytes to actually process the data. So let's go ahead and call process block down here. Simple enough. Actually, I'm thinking we're going to have encode and decode. Let's process block encode. There we go. We can reuse this variable, but let's just make a function that's specific to this one. So process block encode. Hopefully that makes sense what's going on here. We have this function that will get called for every single byte that we read. Once we encounter 3 bytes and we've stored them up, then we will actually process the block of all 3 of those bytes. So this is pretty straightforward. We can do some things here, but let's go ahead and let's just pull the data out of the block. So we want byte 1, which is the block at spot 0. We want byte 2 and byte 3. Then we're going to want to mash it all together into a big number. 24 bits into a number, and Bash has 64-bit integers, so it'll be more than enough to store it in. And then we want to extract the 6-bit numbers out of it, or the sextets, is that what they're called? I think they are, actually. Yeah, they are. Cool. Wow, I pulled that out of nowhere. So, I'm trying to think. It might actually be worth it to make a diagram for this. Let me mess around with that and see what I can come up with, because I think, like, here's what I'm thinking. We have our input, which is B1, B2, and B3. And what that actually looks like is three different numbers. So let's call them A, B, and C. So we have an 8-bit number, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm just going to format that. I'll cut this out. There we go. So B1 looks like an 8-bit number here. B2 looks like an 8-bit number. And B3 looks like an 8-bit number. What we want, our output, will be S1 because we want to make sextets. So we're going to call them S1 instead of byte. We have sextets. I guess that means we should call these O for octets. Whatever. Let's just leave it as S1 right now. Maybe I'll get upset by this later. And that will look something like this. It'll look 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now you see what I'm doing? There's still 8 A's to distribute here, but we have to go ahead and distribute them among 4 different things. So now we have 4 B's we used here. We have 4 more B's. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that looks right. This will be S2, this will be saved as S3, and this will be saved as S4. That makes sense. That's our goal here. Here's the three numbers we have. Here's the three numbers we want. And in the intermediate form, we'll like make some variable just called n. This will be our own 32-bit number in bash, but it'll be to the 24 bits from this. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And bash wants us to make it 1, 2, 3, 4, 5, 6, 7, 8. Let's just think of it as a 32-bit number, padding it with zeros, so it will store all of this. So hopefully this diagram kind of makes sense. I don't know if this is helpful or not, but here's our input. We have these three numbers. We're gonna smash it together into this, and then we're gonna extract the data we need out of it. Beautiful. So let's go ahead and make our n variable here. This is our math syntax here. So we need to take the first byte, B1, and we need to shift it to the left, because B1 is here, which is our A. We need to shift it to the left, not 8 bits, but we need to shift it to the left 16 bits. I don't know if this is helpful or not. We need to shift it to the left 8 times 2 bits, if that makes sense. This might be helpful. And then we need to add it to B2, shift to the left 8 times 1. And then we need to add B3, shift to the left no times, but that looks like 8 times 0. I don't know if the syntax is easier than just doing 16, 8, and 0, but maybe it is. I'm trying to see if I can format this. Here's what it looks like formatted. Basically, we need to take B1 and move it all the way to the left of this number. Not all the way to the left. We need to move it here. So we have to move it over 16 bits. So 1 byte times 2, 1 byte times 1, 1 byte times 0. That's kind of what's happening here. And then we get this big number n. Oh, we're missing parentheses. Huh. I was wondering why the highlighter was yelling at me. There we go. That looks good. So now we need to be able to pull out S1 equals something, S2 equals something, S3 equals something. So we have this variable n, and in order to get A out of it, which is S1, we need to shift it over 6 times 3 spots. So we need to shift it over 18 bits, 6 times 3 spots, and then we need to turn off all the bits except which we care about. That might be a little bit confusing, but we need to take n, we need to shift it over to the right 6 times 3 spots, and then we need to do a bitwise AND of a 6-bit number. There's a couple ways we could do this. We could do OF63, I think, which is the first 6 bits turned on. I think binary, why is it? That was weird. I think binary might actually be easier to understand here. Hear me out. In bash, you can do binary like this, 2, this little pound sign, and then 1, 2, 3, 4, 5, 6. So we're just turning it on with the last 6 bits all set to 1, so everything else will implicitly be 0, and we're doing a bitwise AND here. So this will just leave on the 6 bits of the number. This is very esoteric, but what we're doing, this might be hard to understand, is we're taking this section of A, we are moving it all the way over to the right, we're shifting it over here, so now it's over here, and then we're turning off every other bit to the left of it. It doesn't make, for this A example, it's padded with 0, so it doesn't matter, but for the other 2 examples, like the A bits will be above B, we're turning those bits off. So now we just need to do this 4 times. So this will be S1, S2, S3, and this will be shifted over by 3, 2, 1, 0. I think that's it. Now we have the numbers that base64 cares about. The only thing left to do here is figure out what character to export. So we know the number, it's going to be a number between 0 and 64, 0 and 63. So we're going to need that base64 alphabet. Now the beautiful thing here is that we don't even need to copy it over all manually because we have curly brace expansion. I'm looking at the other screen right now, you guys can't see it, but A.Z. So it's all the uppercase letters, A.Z, all the lowercase numbers, 0.9, 0 through 9, and then it's a plus and a slash. So we have made an array with every possible letter that is used by the base64 alphabet. Pretty cool. So let's make a simple function actually. Because once we get down here, then we can just omit alpha to omit the alphabet character of S1. And then we'll just do this 4 times. So S2, S3, S4. Let's go ahead and implement omit alpha. So this will take an index as the first argument, and then we will simply printf a single character from the alphabet at spot I. That is all we will do here. And this should work. Let's check our work. So let's imagine someone calls main. They call it with the encode mode. So decode is not set to true. They call main, we call process input, and there's a whole bunch of stuff here. We don't need to go through it, but we just call process byte every time we encounter a new byte. Every time we encounter a new byte, we store it in a block. Once that block hits 3, then we go and we emit the 4 base64 characters per 3 input bytes. Notice what we don't do is we don't flush the buffer at the end. So if we don't have a multiple of 3, we're going to miss out on that padding and stuff. We'll add that logic later. Let's test our work. We should be able to echo, let's do printf ABC and pipe it into base64. Here's what it should look like. Let's pipe it into our script and see what happens. Okay. It's wrong. It's absolutely wrong. Here's the beautiful thing, actually. Base64 just puts a new line because you can ignore white space when it comes to Base64 encodings. So we can just go ahead and just once we're done, when are we done here? At the bottom of process input. Yeah, once we're done processing the input, then we can emit a new line here. So let's see. The system Base64 says this. Ours says this. So it's not quite right. It's a little bit right. This part's right, but this part's off. Let's just look for some basic issues. Actually, this is probably a good time to bring up shell check. Warning, S4 is referenced but not assigned. Hey, look at that. Beautiful. So we emit S4. Well, yeah, that makes sense because I didn't update this. You guys in the comments are probably screaming at me. If you like what you see so far and you've made it this far in the video, hey, welcome. That's awesome. Go ahead and hit the subscribe button. Okay, I just hit 111,000 subscribers at the time of this recording. So yeah, hit that button. Let's get that number really big. I don't have any brand deals or sponsorships on this video. Like, we're just doing this for the love of the game. So if you're watching this, you're a nerd, hit that subscribe button. That'd be awesome. You guys think this will work now? Shell check is clean. If we do the system Base64 and we do our Base64, that's pretty good. If we add another byte like an exclamation mark, we get nice little padding there. We don't get that here. That makes sense. We're not draining the final buffer. But what if we were to print something like, I don't know, Dave without the final E? We get this. If we run the system Base64, we get this. That's pretty good. So what we have works. Like, that was surprisingly easy. I'm a little bit scared at how easy that was. All right, so here's what I think we need to do for the padding. Because what we have to do now that we have the process block encode, once we get to the bottom of processing input down here, we have to also process at the block, we have to drain the buffer. So we'll call process block. Yeah, I think we're gonna have to make a process block helper function. Remember how process byte has an encode and decode variant? We're gonna do the same thing for process block. So we have process, I'll show you. We're gonna make a generic process block function, doesn't take any arguments, and just dispatches to the right one. So process block decode and process block encode. So now if we go up here, we have process block encode, perfect. And it's called down here in process byte encode, that's fine. Let's just keep them all generic, process byte. We're unnecessarily checking the Boolean, but let's just keep it generic. We'll use the simple generic functions here. That should be block. Okay. So what this means is after we've read all the input, then we have to drain the buffer. So we call process block again. Which means that when we call it here, there might be 0 items in the block, there might be 1, there might be 2, or there might be 3. We have to account for all that. So we're gonna need the length here, which we can get with this. And then because those values might not be set, let's go ahead and just give them default values of 0. We're pulling the bytes out. If they're not set, we're treating them as zeros because that's what the spec says. And we're gonna differentiate them from an actual null byte, which would also be all zeros, by knowing the length of the block or how many we are to encode. So on the actual RFC, it tells us exactly how to handle this. So the final quantum of encoding is exactly 8 bits. Here, the final unit of encoded output will be 2 characters followed by 2 equal signs. So 8 bits is 1 byte. If we have a block length of 1, we need to emit 2 characters followed by the equal sign. Let's go ahead and do that. So let's do a case over here over len. If there are 0 bytes in there, then we need to do nothing. There's nothing. If there's 0 bytes in that block, we do absolutely nothing. There's nothing else to process. We're draining an empty buffer. If there is 1 byte, which is what we just read, then we need to omit, it says 2 characters here. So let's omit S1 and S2 here, and let's make 2 equal signs, and that's it. Then the spec says, if it's exactly 16 bits or 2, a length of 2, the final unit of encoded output will be 3 characters followed by 1 equal sign. Okay, simple enough. So let's just go ahead and actually just copy this, bring it down here, change this to 2, and this should have an emit alpha of 3, and this should be 1 equal sign. And then 3 means it's a full block, so we will just do everything with no equal signs. So if we have 3, we'll bring this here. Let's fix that indentation. There we go. There may be a way to write this differently where we don't repeat the stuff here, but I think this is fine, actually. It makes it very clear. Oh yeah, and then once we process the block, once we've drained the block, we should actually drain the block. We should reset the block to an empty array. So completely clear it out. I think this works. I think this actually just works. It's a lot of math here. I'm a little bit afraid. So if we print Dav into base64, we get this. If we print Dave, we get this. If we print Dave E, we get this. Dave, I'm just spelling out my name, we get this. Okay, let's go ahead and redo all of that using our base64. We get this. That looks right. Let's print it out with the E. We get this. Hey, that's exactly the same. That's beautiful. We do this. Hey, look at this. That's the same. That's beautiful. That's the same. That's beautiful. I think we have encoding done. We can run our tests now. What I'm going to do for this test is, because I don't want to be discouraged by failures, we're going to do a fun little thing called commenting out things I don't want to see. So we're going to comment out the decoding section. We are just going to run the encoding tests. So if we run the encoding tests, it fails. Okay, let's figure out why. Cat files hello.txt, pipe it into base64, we get this. Pipe it into our base64, we get this. Yeah, look at this. We are ever so slightly off. That is very interesting. I wonder what's going on there. Let's do a nice little shell check on base64 just to make sure. Okay, that seems right. Let me think. Hello is, that file is just HELLO with a new line, right? Okay, so it is that's breaking it. Is it the new line? I have no reason to think this. I'm just totally going on. This is vibes-based debugging. What about a single new line? Okay. But when there's 3 of them, there's an issue here. Okay. Very interesting. It's like the right characters are here. They're just out of order. Am I printing things out of order? Is that what I'm doing? I am. I'm just printing things out of order. All right, guys, here's the secret call out if you're watching my video. Go ahead and put the timestamp in the comments and be like, Dave, you really got to look over your code before you test it, okay? Oh, man. It's got to be frustrating for you guys to watch me program. That looks way better. That looks way better. Beautiful. Beautiful. Look at that. We have encoding, and it is actually working. That is incredible. Do we have some big files we can encode? I think we do. We've used it in a previous video. User share dict words, which I think is a symlink. That's how many characters. Oh, wow. So this is a pretty big file. Do we have a smaller file we can use? That's 2.5 megabytes. That'll probably take a while to do 2.5 megabytes. You know what, actually, I'm not even gonna do that yet. Let's wait until we get decoding, and then I wanna do a big file encoding and then decoding to make sure we can read it back. I think that'll be more fun. So, we have encoding working. Now let's figure out decoding. Now here's the beautiful thing. This should be easy, right? We just have to go backwards. So let's do that. So we have process byte encode. We need process byte decode. And I stubbed out that function, and it is nothing here. Okay, so let's go look at our process byte encode function. All we do is we read a byte, we store it in the block, and if the block grows to a certain size, then we process it. We're gonna do exactly the same thing, okay? We're gonna take the byte as an argument, even though it's stored in a byte. There's only 6 bits of it that are actually relevant to us, but we're gonna store it in the block, and when the block gets to 4, because remember, these are base64 alphabet characters we're reading. Once we have 4 of them, then we can turn it in to 3 bytes. So then we'll call process block on it. This is the generic process block function, so let's go make sure that is set up to dispatch correctly. Process block decode. We don't have that implemented, so let's go ahead and implement that. So we have process block encode here. Let's go ahead and implement process block decode here. And we're gonna steal a lot of the same logic here. So if you remember, we have all this stuff. I'm gonna copy all of this. We're gonna have to make changes, but I'm gonna copy all of this up here, and I'm gonna show you the changes I'm gonna make here. Because what we get from the block when we're decoding is a little bit different. We don't get the B values out of it, we get the S values out of it. Our input and output are swapped here. So I'm gonna go ahead and just swap these. There we go, this is what we get. We get an input of S1, S2, S3, S4. We have to shove it all together and then extract the bytes from it. We just have to undo what we did in the encoding process. So the beautiful thing is with base64 is because it's going to be padded properly, we don't need default values here. I don't even think we need the length. We'll just keep it right now, it doesn't hurt. But I don't even think we need the length. We're always gonna be processing a block of 4. Technically also of 0 when it comes time to drain it at the bottom. So we'll just handle 0 and 4. That seems like the only 2 possibilities here. So this is S2, this is S3, and this is S4. There we go. Now we need to put them all into a big number. I just thought of a problem here. Yep, I totally blanked on this problem. Okay, we do have a problem here where we call process byte. Let me type that correctly. We have our process byte encode and decode. Process byte decode. This is the actual byte value, the number on the ASCII chart. This is the number itself. We don't actually really want the number itself because remember, it's going to be the limited base64 alphabet. So the number on the ASCII chart doesn't matter. We kind of want the number on the alphabet chart. We want a number between 0 and 63, and also to account for the padding. We'll probably use -1 as a sentinel value here. So we need to do a little bit of translation when we process the incoming byte. So let's do a little translation before we add it here. We're gonna turn the byte into the value, and then we're gonna store the value. So the value will be its index into the base64 alphabet. So let's do some checking here. We'll have to check a couple things. I think first we'll throw out white space. We'll just not care about white space. Light mode jump scare in 3, 2, 1. I pull up the ASCII chart. If we're worried about white space, we're gonna worry about ASCII characters 9 through 13. We're gonna throw all these out and also 32. As long as we throw these out, we should be fine. So I need 9 through 13 or 32. So if byte is greater than or equal to 9 and byte is less than or equal to 13, or byte equals 32, then skip white space. We will just return from the function. We won't even store it in the block. We're just going to ignore it. You give us any sort of white space, we are skipping it. We don't care. If the byte is equal, we're gonna have to do some translation here. You know, I was gonna pull up the ASCII table, and then I remembered there was an ASCII command, but it's not actually on my Mac. Can I just brew install ASCII? I remember this command from a while back. I haven't used it in a while. This is so much nicer to look at. This is so much easier for me to process. Okay, here's what we're gonna do. We're gonna look through all the characters we need. So the first thing we wanna care about is an equal sign. If we're reading in encoded data, there's gonna be an equal sign. That's the padding. So if the byte value is 61, then it's an equal sign. We'll do this. We'll mark it so we know. We'll put a comment here so we know exactly what it is, and we will set the value equal to -1. This is our placeholder, our sentinel value for the padding value. If the byte is equal to XX, we'll put that for now. Then we need the plus sign. That's another one we have to look for. elif the byte is equal to, I'm putting some placeholders here. We'll look through the ASCII chart. We'll swap through them. I probably won't make you guys watch all this, but this is basically what I'm doing. We need the slash sign. That'll be something here. And then we need the range of characters. So let's just do this first. Let's grab the plus sign, the plus and the slash. So the plus is 43 and 47. Okay, so if it equals 43, if it equals 47, then the value of the plus sign is, I think the plus sign is the second to last one. Yeah, so this would be index 62 and 63. Yeah. Then we need the uppercase, the lowercase, and the numbers. So the uppercase starts at 65. So we just need to check for 65 and then subtract 65 from it, and that should be the value. So if the byte is greater than or equal to 65, and the byte is less than or equal to 65 plus 26, because there's 26 characters. No, let's just not do math here. Let's just be explicit, because I think I'm off by 1. If we go to Z, it's at 90. Let's just do 90. That's easier to understand. Then this will be A through Z, and the value is the byte value minus 65. Now, the next one we have to check is the lowercase ones. So the lowercase letters start at 97, and they go all the way up to 122. So from 97 to 122. This will be lowercase a and z. And for this one, it's byte 97 minus, should just be minus 65 again, right? So we start at 97. I'm going to get something wrong here. 97 minus 26 characters brings us down to 71. So we subtract 71 from that, and we should get to the right spot. I think that makes sense. And then finally, we need the byte is between the numbers. The numbers are 48, right? That's a different way of looking at them. Yeah, they start at 48. Okay, good. I just had that in my brain. 48 all the way up to 57. Easy enough. Byte starts at 48. 64 minus 2. Base 64 minus 2 because there were 2 other characters there. Minus 10. It needs to go to 52. So it should be plus 4. 48 to 52 is plus 4. I know there's a lot of hand-wavy math there and a lot of trust me, bro. I hope this is right. Basically, we're taking the byte number. This is the actual byte, so this is what it shows up on the ASCII table. And then we're translating it to where that character appears in the base64 alphabet. That is what's happening here. And then if we get down here, then we will fatal invalid base64 byte $byte. And we should probably go implement a fatal function, right? Fatal will be simple enough. We'll just call echo fatal with whatever arguments you give us. Those will go to standard error, and then we'll exit with 1. Simple enough there. Let's go back down here. We push the new value onto the block, and then we process the block when we get to 4. So process block decode. Now that we're here, we are pulling out the index into the base64 alphabet. That is what we care about now. Okay, this makes a lot more sense. The scary thing here is that we have a length, but all the blocks, because of the padding, should always be full, but they might be full of a -1. So we will have to write logic to detect the -1 and figure out how much data we need to process. Yeah. So let's reason our way through this. We should always have at least 2 of them, because if there was 1 byte of input, that fills up 2 of these. 1 is like half full. Well, 1 is actually 1/3 full. But for 1 byte, we should print out 2 of these. For 2 bytes, we should print out 3 of these. And for 3 bytes, we should print out 4 of these. So the first 2 values here should always be greater than -1. So let's do some checking here. Sanity checking. If S1 is less than 0 or S2 is less than 0, then fatal invalid base64 block. Yeah, and then there's some more too. If this one is -1, then this one should also be -1. We should never get in a situation where this has a value in it and this one does not. So if S3 is less than 0 and S4 is greater than or equal to 0, then fatal, impossible base64 padding configuration. That means you had equal sign and then something comes after the equal sign. Yeah, this is tough because if we have some -1s in here, when we go to do this operation and turn to a number, we're gonna break some stuff. Let's just make a note for ourselves to do deal with -1 values. We'll find a way to deal with that, but for now, let's update this code to work. This code just needs to be the opposite of what we have. So instead of pulling out n like this, where we do B1, B2, B3, we're actually gonna just do this, make it 4, and this will be S1, S2, S3, and S4. So instead of shifting it over by 8, we're going to shift it over by 6 because there are sextets, not octets. And this should just be 2, and this should be 3. That should be it. I know that went by fast. That's why I coded this way, so it'd be very obvious what's happening. We're shoving all these S variables together. These are what we have here, and we're creating this giant string with them. This giant number, actually. And I think that's valid. We do have problems with the -1s. We will deal with that. And then from down here, we don't have S values. We are reading out the byte values. So we're doing the exact opposite. We're taking n. We should shift this over by 8, by 8, by 8. And then here, instead of reading out 6 bits, we want to read out 8 bits. I think that's good enough, actually. Well, let's not do 1, 2, 3. Let's do 0, 1, and 2. There we go. Let me just spot check this. I think this is fine. Let's do a little sanity check on what we have. Okay, we are shell check clean. That's beautiful. And I just think we need to deal with the -1s, because here's the thing. If only 2 of the S's are set, we don't want to print all these to the user. We only want to print the first byte because the rest of them will be padded with zeros. Yeah, let's I'm having a little bit of trouble wrapping my brain around this, so I'm going to test out every possible thing I can think of. This is what I do when I start to get a little bit stuck, is we'll do a case in len. This is the length of the block. The block should only ever be 0. It's an empty block. We are draining the buffer, in which case we do nothing. There is nothing to do. No buffer, just exit, just return. It should be 4, meaning it's full. There was correct padding. This is correct. Do nothing. And it shouldn't be anything else. If the length is anything else, then it's a fatal. Invalid decode block length len. Okay, we are just trying to eliminate all the possible ways this can break. Here's our amazing error checking here. Now, when we get down here, we need to figure out how many bytes to omit because there are some -1s here. So here's what I'm thinking. Let's make a variable called bytes, and this will be how many bytes we need to omit. If S3 is less than 0, this means that only 2 of the S's have it. There's only 1 byte for us to process. Then we will say bytes equals 1. If S4 is less than 0, then we need to omit 2 bytes. Else, all of them have positive values or are 0. Then we need to omit 3 bytes. And then down here, we can case over that. So we could say case bytes in. If we want to omit 1 byte, then we will omit byte of B1. We don't have this function yet. If we want to omit 2 bytes, then we will just do this exactly. There's probably a cleaner way of doing this where we always omit byte 1 and then we check if we need to omit byte 2 after, and then we check if we need to omit byte 3 after. But for now, it's a little verbose, but I like it. It'll cut down on any possible errors I could think of. 3, and this will be B1, B2, B3. So we do need to implement omit byte. We still haven't dealt with the -1s, so if S3 is less than 0, then S3 should be set to 0 and S4 should be set to 0. If S4 is less than 0, then S4 should be set to 0. I think that's it. Let me shell check just to make sure. That looks fine. Yeah, I think that's good. We just need to omit a byte now. And wait, no, hold on, there's still more. At the end of process block, Yeah, we have to reset the block. We have to completely empty it, get rid of it. Actually, yeah. Yeah, I'm trying to think if we should move it to the generic function or not. I don't know, but we'll reset the block there. That makes sense. Now we need to emit byte. This is where we take a number and then we turn it into the underlying byte. There is a nice little printf trick for that. We've done that a million different times on this channel, but I'll pull up the MD5 script that does it, because there was a nice little printf trick. And of course I have to find it. Oh no, we didn't do it in the MD5. We did it in the, did we use it in the JSON var? I think we did. Here is where we do it. Okay, this is quite the hack. I'm gonna copy this code in and I'll show you what is actually happening here. Because it's totally hacky, but it absolutely works. We have our byte and we have local hex. Let's do that. So we take the byte, which is a decimal number that represents the byte we want to emit. We convert it to hex, %02x, whatever that number is. So we have $I here. This should be $byte. Now we've converted into a hex string. This is a %, a literal, like the number padded with zeros and the literal x here. Then we pass it to printf using this magical %b format specifier, which will turn this into the actual byte. Might be a little bit confusing. In bash printf, this %b extension expand \escape sequences in the corresponding argument. So we can do printf %b, and then we can give it something like x05x like this. And if we pipe it to a hex dump, we can see that we get 0578. That's not right. This needs to be a double slash. No, it is right. I'm lying to you. I just put an x here at the end of it. There we go. So whatever number we give it here, like 45 is hex, it'll show up as 45 here. So this is how you turn a number into the actual byte using bash. Super cool. So we store it into this hex representation and then we just output it to the screen. And this should just work, right? I'm a little bit skeptical, as you can tell, of this logic. So let me study this real quick. Once we have a block to process, we get the length of it, which I don't even think we use. S1, S2, S3, S4. We pull the 4 S's out of it. We do oh yeah, we do use the length. We do a lot of checking. Okay, it should be a 0 or 4 buffer. It should always be valid. And then if S3 is not something we should consider, then we set both these equal to 0 and we only emit 1 byte. If S4 is something we should consider, we set it to 0 and then we only emit 2 bytes. Otherwise, we emit all 3 bytes. We calculate our bytes here by reversing the process we did while encoding. We output them to the screen, and then we do that, right? I think that's right. Yeah. So here, let's echo hello, pipe it to base64. We get this. Pipe it to base64 minus D. So that's not right, but it kind of looks right. like it kind of looks right, you know what I mean? Like, is that good enough? Let me look for some obvious issues here. Times 2 times 1 times 0. 6 times 3, 6 times 2, 6 times 1, 6 times 0. S1, S2, it's in the decode the problem's going to be. So when we're decoding it, S1, S2, S3, S4. I'm just making sure all my variables are correct. 6 times 3, 6 times 2, 6 times 1, 6 times 0. Yeah, look at this. Guys, I'm a good programmer, dude. I swear, like, I'm actually a good programmer. You guys would be blown away if you knew how good I was at programming. That looks good. There's an extra new line. We are emitting a new line somewhere. Yes, we are. Yes, we are. We are emitting a new line at the bottom of process input. Do you remember? I put it down here. We drain the buffer, and then we emit a new line. We don't want that. If we are decoding, then we don't want the echo. So if not decode, I think that's what we want. That looks better. There we go. Okay, so when we encode, we put the final new line there. When we're decoding, we don't do it because we have all the data we need. Guys, what do you think? Do you think this is going to work? Let's go ahead and uncomment this because I'm not afraid anymore. I was scared before, but I'm not scared now. So let's see if this actually works. Test base64. Dude, yo, dude, this is amazing. Okay, first of all, also, that 4 kilobyte file, that just flew by. That was so fast. That was so incredibly fast. That just works. That's insane. Okay, Let's try and encode a bigger file. What do you guys say? What are some big files, I think? Do I have bin bash? That's a 1.2 megabyte file. What we can do is we can use PV like we used before, which is our pipe viewer. So PV bin bash, now we know the file size and we can get a progress bar. Let's pipe that into our base64 encoder, and let's write that to bash.b64. Okay, 13 seconds. It's still at 13 seconds. Now it's at 41 seconds. I guess it's, well, you know, 30% of the way done. Not terrible. Like I said, guys, it's not the fastest, okay? There are definitely probably ways to speed this up. We're doing a lot of math before we determine if we even really need to be doing that math. That's probably something that could be sped up here. We can join a bunch of the math operations together. We can even profile this a little bit to kind of get an idea of where it's getting stuck. But yeah, this is wild. Okay, so we have created a base64 representation of a 1.2 megabyte bash binary. And it looks like that. Let's go ahead and cat the entire thing to my terminal. Okay, I see a lot of like A's, but wow. There you go. You guys ever want to see what bash looks like? That's what it looks like, is base64. So the real question is now, can we do, let's PV that bash.b64 file, and we will write it to base64 minus D. We'll decode it into bash, a new file in our directory called bash. So we're going to decode it. We'll see if decoding's any faster. ETA seems a little bit higher. We're only at 12%. I can't tell if that's fast or not. It looks like the speed is actually slightly slower. So yeah, like I said, guys, this isn't going to be the fastest thing in the world. Okay, we're in bash. This is not the right tool for the job. But if you like what you're seeing, go ahead and hit the subscribe button. Let's do it. If you made it this far, you've earned it. Or I've earned it. Whatever. Yeah, I'll cut this when it comes back. Okay, so now we have a binary called bash. Shows up as a binary. Let's go ahead and MD5 it. Let's MD5 bash here and then bin bash on my system. And they are the same. They are the same. We are able to round trip successfully a 1.2 megabyte executable binary file using bash's base64. That is wild. Now the funny thing is, if we were to do both in one step, I think it will actually be just as fast. That sounds crazy, but like, so I'll RM these files, bash.b64. If we do pv-c, because we're going to do a bunch of them, bin bash, pipe that into base64, pipe that into pv minus c, and pipe that into base64 minus d, and then write that out to, we can just write out the dev null, it doesn't actually matter. Both of them will be running, and we can kind of get an idea of how fast they're each going. But it should be the same amount of time because it'll just go to two separate threads. Two separate processes should be running these instances of bash. So yeah, the first one knows the ETA because it knows the size of the file, is able to stat it. The second one has no idea because it's just receiving its input from standard in. And the way PV accomplishes the minus C argument is actually incredible. I'll talk about that in a future video. I think it's really neat. But yeah, notice the output's only ever going to be blocked by how fast the input is going. So yeah, like once this one finishes, the next one should pretty much be finished. Like it's not that far off data-wise. That's really cool to see. This is a really cool view into it. So the encoding finished. Now the decoder is running. We can kind of get an idea of how long does it take. I think this will have to go up to 1.23 megs. So the decoder does take a little bit longer to run. We weren't technically blocked on the input that much. That's cool to see. Oh, right. Never mind. Yeah, the decoder has to read more data because when you base64 encode something, it actually gets bigger in size. I didn't think about that. Yeah. For every 3 bytes, you're outputting 4 bytes of character. So what does that mean? Is it 33% bigger? 25%? 33%? I don't know. Some nerd in the comments can correct me. That's incredible, from 1.65 to 1.23. Yeah, it looks like it's 33% more of data that we had to process. Interesting. That's really cool. But it works. That's kind of beautiful, isn't it? Now, why did I decide to write it to dev null? Why didn't I just write it to MD5 like I did before? I have no idea. I don't know what I was thinking. Because if I were to MD5 bin bash, then I could do this. And instead of writing it there, I could write it to, well, I could write it to PV minus C. And then I could pipe that into, you know what? Let's have a lot of fun here. Let's pipe it into my MD5, my bash version of MD5. How's this? Now we're going to have 3 progress bars. So here's encoding the base64 data, here's decoding the base64 data, and here's calculating the MD5. Wow. That's hilarious. So let's let this run and see what the MD5 says. Hopefully at the end of all this, this is what should get printed. C223F27, whatever. That's what we should see at the end of this. I'm gonna let this run. Look at that. That is beautiful. C223, blah, 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 blah. 14 ABC, 14 ABC. That's it. That's good. That's awesome. We have a working base64 implementation in Bash that's being piped to our MD5 implementation in Bash. I don't know why you guys watch this channel, man. Don't use these tools. These are just for learning. This is just for fun. If we shell check our base64, we're good. If we shell check the tests, I didn't actually do that. We never actually invoked the cleanup function. It doesn't detect that it's trapped. Whatever. Sure. I don't care. Beautiful. That's awesome. That is great. And yeah, that's all I got for you guys. Thank you so much for watching. Of course, I can't end a video without thanking my subscribers. Nope, that's not right. Well, I will thank my subscribers. Thank you guys. I also want to thank my patrons over at Patreon. Thank you for your continued support. Check this out. Look how insane you guys are. You guys have found a way to put ANSI escape sequences in your name, and Patreon doesn't filter them out. I don't filter them out, so you can make my terminal do wild things. Thank you so much for your continued support, guys. I appreciate it. I think it's super cool. And yeah, you guys are awesome. If you want your name at the end of my video, yeah, go check out the Patreon. I don't have any exclusive content there. It's literally just a chance to get your name at the end of my video and have some bragging rights. That's pretty much it. And so many people have signed up for it. You guys are awesome. I think you guys are great. And yeah, thank you so much for watching. I appreciate it. That's all I got for you guys. Have a good night. I'll see ya.